Alright, now we're back in section 3 here, talking a little bit more about logarithms. I mentioned in the previous video that a base 10 logarithm, which we can write without even the base written down, is known as a common log, base 10 number system. Well, we know that e is the natural base, so a base e logarithm, which we don't have to write in this form, we can abbreviate it ln of x, logarithmic naturalis, okay, is a natural log. And those are the two logarithms that you'll find on a calculator. You won't find a base 5 logarithm button on your calculator unless you have a really fancy calculator. These are the two types of logarithms that we do most of the computation with. Now, up to this point, when I've tried to evaluate a logarithm, I was very fortunate in that I could write the expression having the same base as the logarithm. Look down here at these 4 examples. This is a base 10 number, base 10 logarithm. This can also be thought of as the log base 10 of 10 to the 1, 2, 3, 4, 5, 6, 7th power. Now what is this saying? This is saying 10 to what power is 10 to the 7th? Well, this is equal to 7. If I can match the bases, it's easy. I don't need a calculator. I can do the arithmetic in my head. Here's another one very much like it. This is the log base 10, another common log, of 1/10 or 10 to the negative 1st power. Base 10, 10 to what power is 10 to the negative 1? Well, that's negative 1. If I can match the bases, I'm in good shape. Well, this is a natural log. This is log base e of e to the 5th. So e to what power is e to the 5th? It's equal to the 5th, equal to 5, almost to the 5th. And then this one's not much different. It just doesn't have the exponent written down. It'd be like an exponent of 1 here. So this is the log base e of e to what power? Well, to the 1st power, e to what power is e to the 1st? It's equal to 1. If we can match the base, we're in great shape. However, that's not always the case. As you can see in the next example, it says to approximate the logarithms. Now, can you write, this first one here is a common logarithm. Can you write 229 as 10 raised to a power? I'll let you think about it for a second. The answer is no, you cannot. So I'm going to grab my calculator here and I'm going to approximate this. Now I'm using a TI-89. You know, any scientific calculator will do this. And I'm going to find the common logarithm. If my eyesight improves a little bit, I'll be okay here. Good Lord, I can't read to save my life here. I'm so used to using a scientific calculator. So I've got to figure out what the common log is here. I may have to go to my, good Lord, where is the common log? Alright, well, you can just ignore me. Alright. Well, I may have to go to my catalog here for a logarithm and see if I can find it here. And, oh, thank heavens I found it. The common log of 229 is 2.3598354. It's an irrational number, but the 4 decimal places, it is, good Lord, I hit a button here. Let me try it again. Approximately 359898. Next time I write this down on a piece of paper. Alright, now we're going to find another common logarithm here. So let me go back to my catalog. And I am going to go to 0.0216. Well, if I had half a brain here. Let's try that again. The logarithm of 0.0216, and I get negative 1.6655 to 4 decimal places. Alright, well the good news is, and that's an approximate, the good news is that the logarithm, the natural logarithm of 87, on my 89 I can find the natural log function a lot more quickly, 87, and it is approximately 4.4659 to 4 decimal places. Now, when you see a logarithm written in this form, the decimal part with a positive number, the decimal part here is called the mantissa. The whole number part is called the characteristic. And you will find in your lesson a video that shows you how to find logarithms using logarithmic tables, which we had to do before calculators came around about 45 years or so ago. Okay? Now, when you have a negative number, the mantissa has to be positive, so we would have to rewrite this as negative 2. Here, let me put it down below. Negative 2 plus 0.3345, so that we would have a positive mantissa, and then this would be the characteristic. Those were the days. Now, let's get to the basic properties of logarithms. There are several properties of logarithms that we're going to be needing. These first ones here are fundamental, that the log base b of 1 is always 0, because if you take the base to the 0 power, you get 1. Log base b of b is equal to 1. Again, because if you take b to the first power, you're going to get b. Log base b of b to the x equals x. If you bring this over and change it to exponential form, you get a true statement, b to the x equals b to the x. And in this case, if we change exponential form into logarithmic form, we're also getting a true statement. This is because these two guys here, these are inverse functions. I'm composing the logarithmic function and the exponential function. The logarithmic function and the exponential function. In this case, the exponential function is the inside function. In this case, the logarithmic function is the inside function. When you compose them, you get, for inverse functions, the identity. You get equal to x. All of these are useful to memorize. In fact, look right here. Log base 13 of 13, that was easy, that's 1. Log base, this is base e, remember, when it's a natural logarithm written this way, of e is, you got it, 1. Now look at this guy, and look at this guy. See how the bases match? The bases match, so I get 3. So I get the bases match, so I get 6. Those are good properties to remember, very useful. Alright, we're going to finish off this video with a couple of graphs. Now I'm going to do more graphing because these are very basic graphs. I'm going to do graphs that have transformations involved, shifting, reflecting, and all that as well. But in this case, I think I'm better off, since I'm not used to plugging in numbers here, I think I'm better off if I think of this as x is equal to 2 to the y. Because this is the equivalent exponential form. So with x and y, instead of plugging a bunch of numbers in for x, I'll plug a bunch of numbers in for y. 2 to the negative 2, 1/4, 1/2, 1, 2, and 4. So if I graph these points, I have 1/4, negative 2. I have 1/2, negative 1. I have 1, 0. I have 2, 1. And I have 4, 2. And look at this graph, where it has a vertical asymptote of the y-axis, x equals 0. Now, it wasn't that long ago that we graphed this. Y equals 2 to the x. And the graph looked a little bit like, this is going to be really rough, and I'm going to make it dotted here, but it looked a little bit like this. Do you see that since these are inverse functions, we know graphically that one is a reflection of the other in the line y equals x. And this certainly looks the case. Now here I have one that's got a base that's 1/2, a fraction between 0 and 1. So let's see what happens here. I'm going to rewrite this as x is equal to 1/2 to the y power. So I create a t-chart here of x and y, negative 2, negative 1, 0, 1, and 2. Plug negative 2 in, 1/2 to the negative 2 is 2 to the 2, or 4. To the negative 1 is 2, to the 0 is 1, 1/2, second power 1/4. So I plug in for the y, solve for the x, much simpler because of the way it's written, x in terms of y. And I graph these points, 4, -2, let's see if I have that, there we go, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. Wait a minute, hang on. 1/2. Okay, that looks right. I looked a little cockeyed there for a second, and the graph goes something like this. Again, the y-axis serves as a vertical asymptote here. Try to make it close to it, but not touch it. I didn't do a very good job. My hand's a little shaky here. Hopefully you'll do better on paper and pencil. Now, if I was to graph, and I have done this before, if I graph y equals 1/2 to the x, I mean, it's kind of rough, but essentially what the graph looks like is something like this. I'm going to try my best. And you see how the one, again, is a reflection of the other in the line y equals x. These are inverse functions, and the graphs would make sense that they would be reflections like this. Remember, exponential functions and logarithmic functions are both one-to-one functions, and they are inverse functions of one another.